So today I'm going to talk about high dimensional space and how to visualize it and think about it, in particular using projective geometry. Now, my goal is to make this as simple as possible. So I'm going to really minimize the number of equations we'll see. We won't see more than a handful of equations. And I'm going to rely mostly upon visual arguments because this is all about space. We ought to be able to do most of it in a visual manner. And so, firstly I'm going to talk about how you can make pictures of these high dimensional objects. And then later, I'm going to talk about how you can do various other operations in these higher dimensional spaces. So, we had lots of fun in the projective plane, the 2D space, looking at things like projections from one shape to another, or these conics which can be generated, or this wonderful sort of duality that existed between points and lines. And it turns out that we can do just the same kind of very interesting transformations in 4-dimensional projective space, 5-dimensional projective space, etc. It all generalizes. And so I'm going to use some visualization techniques, use some computer graphics, and show you how to look at these different scenarios. For example, these quartics, which are a sort of generalization of conics like hyperbola and ellipses and things. I'm going to show you what they look like when they're generated in the 3-dimensional space. I'm going to be talking about homographies, which are basically kind of projections which can occur in higher dimensional space. I'm going to be talking about duality. I hope you enjoy it. So, what is a 0-dimensional space? It is a point. And now I'm going to draw a family of different shapes, of different dimensions. So, the 1-dimensional member of this family is a line. The 2-dimensional member is a triangle. And the 3-dimensional member is a tetrahedron. So what do these shapes have in common? Well, the 0-dimensional one just has one point. The 1-dimensional one has 2 points, connected as much as possible. The 2-dimensional one of these has 3 points, each connected to each other. The 3-dimensional one, 4 points, all interconnected. So these shapes are actually called simplices or simplexes, and they're very fundamental in the study of geometry because they're really the kind of smallest and simplest kinds of shapes of a given dimension. So, can you guess what the 4-dimensional simplex looks like? Perhaps you'd like to pause the video and see if you can draw it. Well, okay, I'll have a go. We now want to have 5 points. And if we simply interconnect them all, then that will give us our four-dimensional simplex. So this is sort of like a triangle in 4 dimensions, if you like. And I think it's fairly easy to see how one can carry on this sort of pattern. One could draw a hexagon, connect all the lines, and that would be a 5-dimensional simplex, and so on and so forth. So this is one kind of class of shapes which we can extend into higher and higher dimensions. And there's another one which is, in a way, perhaps more useful, because mathematicians have a tendency to like to think of things in terms of perpendicular coordinate systems, squares and cubes. Those kind of objects are very appealing. So we're going to think about how to draw a so-called hypercube. The starting point of this exercise is similar to before. We start with a 0-dimensional thing, a 0-dimensional space, and then how do we create our 1-dimensional space? We take our 0-dimensional space and we shift it in a new direction, to the right in this case, and we see what kind of shape gets traced out, and indeed a line gets traced out, which is our 1-dimensional space. Now we just carry on this kind of process. So to get our 2-dimensional space, we get our 1-dimensional space and shift it in a new perpendicular direction. So we already know about the directions of left and right, but downwards is a new direction. So if we shift this line downwards, it will trace out a square. So now we know about left, right and up, down. If we move the square in a new perpendicular direction, say forwards, well then we'll get the cube. Okay, so another way you can think of this is that to get a cube, you take 2 copies of the square and identify corresponding vertices. So for example, this vertex here appears here and here, and we have to join those 2 vertices by a line. Okay, so how do we draw the hypercube? Well, we're going to take the cube and we're going to shift it in yet another perpendicular direction. Let's now draw the hypercube. Just before I do that, I want to say that I can draw this cube here in a simpler way, distorting it a little bit, like so. Now, to draw the hypercube, I should draw a cube, I shall shift it in a new direction, and then I'll just connect the corresponding points. And there we have it, our hypercube. And we can just continue this process. If we want to make a 5-dimensional hypercube, we can just take 2 copies of this and connect corresponding vertices, and we can go on and on and on. So, in fact, the simplexes and the hypercubes are rather special kind of graceful kinds of shapes in 3 or more dimensions. And you might know about the platonic solids, the dodecahedron and icosahedron and so forth. They're very graceful shapes in 3D. It turns out that there are other very nice shapes in 4 dimensions. I'm not going to talk about that now. I want to talk about some other ways that we can think about 4-dimensional space. Okay, so let's start talking about projective space. And we're going to go into higher dimensions. Let's start with one-dimensional projective space. What is it? Well, we talk about the projective line, but in fact, the definition of the one-dimensional projective space is really the set of all lines through the origin in ordinary 2D space. So this is a very funny thing to call the projective line. Maybe the word star would have been a better description. But the thing is, we can think of this as a line in a sense, because if we draw some line going over this, well, these lines exuding from this centre, a lot of them are going to be making contact with this red projective line. And so we're going to get these points. And these points are essentially representing the black lines. So, okay, from this you can kind of perhaps see that this is actually quite like a real line, because if these black lines are densely enough distributed, then you're going to have a sort of continuum or maybe just rational numbers or whatever, some kind of really dense packing of blue dots on this red line. However, what is interesting is what happens when you go very far away to the right or left. You see, think about these black lines. I'll just draw some more. Think about, let's say, this one. Well, okay, that intersects the red line fairly far to the right. What about this one here? Well, okay, conceivably this one, which by the way is the same as this line here, it's all one line. Conceivably this will intersect with the red line, you know, maybe a few miles to the right or many units to the right. But what about the absolutely horizontal line? Well, according to Euclidean geometry, we'd say that that line never intersects with the projective line, but it's far more beneficial for our theory to say, well, let's think of this horizontal line here as intersecting with the projective line at infinity. And that makes a great deal of sense, because if you imagine these black lines tilting, so you imagine that they're rotating around like this. So as this point rotates down, the blue point goes further and further to the right, and eventually this black line here is going to become horizontal, and it's going to continue to rotate, and so it's going to eventually come up like here and appear on the left hand side. And so we actually see that the projective line has quite a few similarities to the circle, in fact, in the sense that, well, very, very naively speaking, things can go off to positive infinity and, you know, essentially go through negative infinity and come back from the other side. Okay, so the projective plane then has some very interesting features. So, the thing about the projective plane, the main way in which it varies from the Euclidean plane is that every pair of lines must meet somewhere on the projective plane. Why? Well, we can actually see this again by noting that the projective plane is really, or can be thought of, from a high-dimensional perspective. So actually it's nice to think of it in three-dimensional space. And now these can be coordinates x, y, and z. And let's say this plane here, this plane is z equals 1. Okay, so the projective plane is essentially just floating one unit above the origin of this 3D space. And now what we're going to do is something quite similar to before. We're going to look at a load of one-dimensional subspaces coming out of the origin. I should draw them red this time. So there's going to be a great mass of these different lines, and you can see that each of these lines is essentially going to represent a point on the projective plane. So a line in the projective plane, there's a line in the projective plane. What does it mean in this 3D picture? We know what it means in the 2D picture, it's just a line, but in the 3D picture, it actually corresponds simply to a plane that goes through the origin. So, and it'll cut out here. And this will be the, whoops, better do a different colour. This will be where this yellow plane cuts the z equals 1 plane and actually forms a line. So, in addition to thinking of all of these lines sprouting out of the origin in 3D space, we think about all the planes that go through the origin in 3D space, the so-called two-dimensional subspaces. And each of those is going to cut this z equals 1 plane at a line. And so, basically then what we have is that so let's denote the projective plane as p squared. So points in p squared correspond to lines in this 3D setting, and lines in the projective plane correspond to planes in the 3D setting. So we have this yellow plane which cuts this green line, and imagine we have another plane which cuts this blue line. So we have these supposedly parallel lines. Now, we can have a point on the green line, which would obviously be represented by some thing coming out of the origin, which I should draw in black this time. Similarly, we have a point on the blue line and a corresponding point through the origin. Now what we do is we're going to move these points to the right. And it's kind of similar to before. As we do so, these lines are going to rotate. And eventually, these lines are going to rotate so much that they're actually going to end up being, well, first this should be like this, later on this should be like this, and eventually they're actually going to lie within the XY plane. So remember, behind this diagram we had the Z-axis, the X-axis and the Y-axis. So there is indeed a plane where Z equals 0. And if these red points move far enough, then the kind of black lines that go through them or get all sort of in the limiting case start to get very close to this Z equals 0 point. And so what we actually say then is that these parallel lines actually meet in this limiting case where these sort of black lines that go through them end up lying within this XY plane where Z equals 0. So this is very interesting, I think, because what we have then is that we have that parallel lines meet at infinity. But it's more interesting than that, because any set of parallel lines, we might have 100 parallel lines, they're all going to meet in the same place at infinity. And if we have a set of other parallel lines in a different direction, well, they're all going to meet at a different point at infinity. So what we actually have around the projective plane is a sort of great circle at infinity, which sort of holds all of the places where different direction parallel lines meet. And actually, I mean, it's very sort of elegant, I think. We could think of this as the circle at infinity, but I think it's more logical to think of it as the projective line at infinity, because what is an infinitely large circle? Well, it basically looks like a line, and since we're on the projective plane, this should be a projective line as well. So the projective line has a kind of far out projective point. The projective plane has a kind of far out projective line. One can carry on this analogy up through higher dimensional projective spaces as well. So one could imagine that the three-dimensional projective space has a kind of infinitely large sphere at infinity, or if you like, a kind of projective plane which wraps around it. Okay, so now we're going to graduate to a discussion of r-dimensional projective space, and we shall just denote this by SR. And we'll suppose r is greater than or equal to 2. So how should we think of SR? Well, we can think of SR as a set of points and SR contains various subsets. A subset is just a set inside a set. And these subsets are called subspaces. I was talking about the subspaces before when I was discussing lines going through the origin in the context of defining projective planes. Please ignore that discussion for now. These subspaces I'm talking about are related, but not sufficiently so. So it'd be better if you don't get confused. Just think of these as different objects in their own right. So there are subsets of SR like this one here, SH, called subspaces. And in fact, there's one of those for every integer h that's between -1 and r. And moreover, SH is H dimensional. So we write that in shorthand. We say the number of dimensions that SH has is equal to H. Similarly, we could have written that the number of dimensions that SR has is equal to R. Okay, so how do we think of this? Well, let's imagine 3D space. In that case, R would be 3. And there are various, so we're talking about projective space. All of these spaces and subspaces are projective. So they're all going on forever in a way. There's no boundaries. We're not talking about cubes or solids or anything. We're talking about these infinitely extendable projective spaces. And when R equals 3, well, yes, we have the full 3D space, but we also have planes. They are subspaces of dimension 2, so we'd call those S2. Lines would be S1. Points would be S0. Okay then, so we can really think quite a lot about these subspaces just in terms of thinking about how they can combine with each other. Given a subspace that's I-dimensional and a subspace which is J-dimensional, we're going to have that the intersection of these two subspaces, which is denoted SI cap SJ, is also going to be a subspace of SR. Just like if you have a line in 3D space, that's a 1D subspace, and a plane in 3D space, that's a 2D subspace. If those two intersect, they intersect at a point. A point is a zero-dimensional subspace of the 3D space. So that's making sense of our intuition. So we have this intersection operation. The only other important operation we need to consider is this so-called span, the span of two subspaces. So the span of SI and SJ is written like this: SI plus SJ, where the plus is circled, and it is the intersection of all the subspaces of SR that contain SI and SJ. Okay? Well, okay then. So I'll tell you a formula now, which is quite useful. I have two formulas to tell you.
One is well known, and the other one I sort of found myself, so I don't know if it's well known or not. So this is the well known one. It is that the dimension of SI plus the dimension of Sj is equal to the dimension of the intersection of these two spaces plus the dimension of the span of these two spaces. So essentially what this means is that if you have a couple of these subspaces intersecting, and you can work out what the dimension is of the subspace in the intersection, well, then you know enough information to work out the span dimension, because you know this, and you know this, so you can work out this, or vice versa. Okay then, so the question I set about trying to understand was, what kind of dimensions can the subspace formed by the intersection of two subspaces have? Okay, so here's my claim, which I think hopefully solves this problem. I claim that the subspace formed by intersecting these two can have dimension k if and only if we have the following holds: that the maximum between I plus j minus r and -1 is less than or equal to k, which is itself less than or equal to the minimum of I and j. So what this result essentially says is that whenever we have SI intersection Sj, it's going to have a dimension k which falls between these limits. And also, kind of conversely, whenever we have an integer k which falls between these limits, we can find a way to intersect these subspaces to generate something of this dimension k. So let's try this out, shall we? Let's test this hypothesis. Perhaps we can look at something a little bit more exotic, like r equal. Well, let's start with what we know. We'll start with r equals 3. So r equals 3. What about the intersection of two lines in r equals 3? So that would be I equals j equals 1. So what does this tell us? It tells us that our possible dimension k has to be between these two limits. The lower bound is going to be equal to 1 plus 1, take away 3, which is minus 1. And the upper bound is 1. So in other words, we have the dimension of the intersection of two lines in 3D space is either going to be -1, 0, or 1. How is that the case? Well, it could be possible that these two lines just miss each other entirely. Then, in that case, their intersection is empty, which leads to a dimension of -1. It could be the case that these two lines intersect at a point, which is a zero-dimensional subspace, or it could be the case that these two lines are actually in identical positions, in which case S1 intersection S1 is actually a one-dimensional space. Okay, so let's apply our formula to a less intuitive case, four-dimensional space. Let's look at the case where we have two planes in 4D space and we're thinking about how can they intersect with one another? What kind of dimensional subspaces can get created? Well, we just plug the numbers into our formula. So I equals j equals 2. There are planes. R equals 4 is our ambient space. So our lower bound for k is just going to be equal to 2 plus 2 take away 4, which is 0. And our upper bound for k is going to be equal to 2. So essentially what we have now is that the dimension of a couple of planes in 4D space is either going to be 0, 1, or 2. So let's start with a familiar case. A case we've seen happen in 3D. That's where the intersection of these two planes is one-dimensional. Well, we've probably all seen this happen before. We have a couple of planes. And the intersection between them is a line, a one-dimensional subspace. So we've seen that happen before. What about this case where the subspace has dimension 2? Well, that's fairly easy to achieve. We can just have the 2D plane being identical to the 1D plane. Sorry, to the other 2D plane. And then their intersection has dimension 2. But what about this? How can we have two planes that intersect only at a point? It seems crazy, but remember we're in four-dimensional space here. So, to see how this kind of makes sense, if you think about this picture here, and think about this line, this yellow line. Well, let's say you picked a point on this yellow line, and then you just tilted, say, this blue plane about this yellow line in the sort of fourth dimension. Well, that would destroy this line of intersection, but preserve this point of intersection. And therefore, we would have, as a result, that I guess we'd have something like this, where the only intersection is this green point. But now I want to talk about one more subject, well, a couple more subjects, which I think are absolutely fascinating. One is duality, because the notion of duality extends to these high dimensional spaces. And the other one is the idea of homographies, which you may have heard of using a different name, the word projectivity. Those two words basically mean the same thing. Okay, so one of the nicest things that occurs in projective geometry is this sort of duality. One sees it happen firstly in the projective plane, where you would have, if you have 2 points, well, let's start with 2 lines. Then they will intersect at a single point, always, because in the projective plane there's no chance for them to miss each other. We can write this in our language as saying that S1 intersection S1 is equal to S0 in this case. Now, the kind of dual idea of this then is that if we have 2 points, then we can always find a unique line between them. By the way, for these to work, these lines have to be distinct. And these points have to be distinct. Anyway, in this case, we can find a unique line that goes between these 2 points. And what that really is the span of S1 and S1, of S0 and S0. So we have that S0 span S0 equals S1. So we can take this and write it under here, and we see the kind of symmetry going on here, replacing the span with the intersection and the zeros with the ones. We have this kind of duality in the algebra. But it goes much further. In fact, it works, there's this kind of duality holding within all different projective spaces of different dimensions. And the key formula is that, say we have r-dimensional projective space, well, for subspace Sn is going to be the dual of the subspace r minus n minus 1. So let's look at this case where we have 3D space. Well, in this case, say we put n equals 2, so n equals 2 gives us that S2 is dual to S3 take away 3 take away 2 take away 1, which is 0. So in other words, we have that in 3D space, planes are dual to points. And what about if we have n equals 1? Well, in this case, we just have the S1 is dual to S1. So that's no problem. And so we have this rather interesting 3D case where it's the points and the planes which are actually dual to one another. And in fact, this has inspired a lot of work to try and understand this kind of counter space where one tries to flip a lot of one's assumptions about 3D space, and rather than thinking of objects being made out of points, trying to think of them as being made out of planes. Well, the literature I've recently been looking at is it uses a different word instead of projectivity. So rather than saying projectivity, they use the word homography. And I like this word more. I mean, it makes more sense if you break it down. Homo meaning the same, graphy kind of meaning drawing. So a homography is basically the same thing as a projectivity. And when we're sending the same kind of shape, you know, like the same dimensional shape to the same dimensional shape, if we do a long sequence of perspectivities, we can get our homography. So then the question just becomes, well, what's the perspectivity? And I shall show you. I'll show you in the two-dimensional case for a start. So suppose r equals 2. And we have a plane here, P, and a plane here, Q. And to do the perspectivity, we need a centre of perspectivity. So let's call that V. And now it's really very simple. if we take any point, let's say A, and we're interested in what its image is under this perspectivity, we just draw a line through A and V and see where it intersects. See where it intersects this plane Q. And we do similar for all the other lines. So we get this bijection from one plane to another just using the single centre of perspectivity. So really it's fairly simple. So this is the idea of perspectivity when r equals 2. Now, there's another idea which is well worth bearing in mind, and that is where you have some sort of generic set of points, I shall call S, maybe a single point or whatever. And you're interested in doing something like a perspectivity or something kind of projective onto a plane Q. Well, if you have a centre of perspectivity, you can just do pretty much the same operation. Now, here I think is the really interesting bit. Remember, oh actually no, sorry to disappoint you, I have to say one more thing before I get to that. And that is that a sequence of perspectivities composed together, as in you combine them one after another and count them as one function, that sends some I-dimensional subspace to some possibly other I-dimensional subspace is a homography. How do you do a perspectivity from a cube, a 3D space, to a cube? Now remember, you have to do a bijection, you have to set every single point on the cube to the other cube. And remember how we did it before. When we had two-dimensional things, we had to make use of the sort of ambient three-dimensional space. So given that, does anyone have any ideas how to do this? Maybe you'd like to pause the video and think about it for a while. Because the answer is really quite nice and elegant. Okay, so the answer is that we should embed, okay, so we'll call this cube S3. We don't have to imagine it being bounded. We'll call this S3. Well, S-3 perhaps. It could be different. So we're going to embed S3 and S-3 in S4. We're going to set R equals 4. Our ambient space is now going to be four-dimensional. So, how is this going to work? Well, all we have to do is just have this 4D space, which I shall try and draw as a hypercube. There we go. And then we're going to have these two different cubes. I'm going to grade them over a bit. There they are. Okay. So we have these two different cubes. S3 maybe S3 dash over there, and all we have to do is add a center of perspective V, and now since we're in 4D space we can just draw all the possible lines from points in S3 that go through V that land in S-3. And remember, these aren't really cubes. These are 3D subspaces. They're big. Not as big as a hypercube, but they're unbounded. And so we can do this kind of bijection. So this gives you the perspectivity. And multiple perspectivities give your homographies.
Okay, so I just wanted to finish with a couple of animations to show some of these ideas. This animation here is a red ring and a green ring with some different homologies performed on them. Now, I did not create these homologies in the fancy method which I've just been discussing. I actually used a kind of algebraic method involving homogeneous coordinates. And so as I drag these different markers around on this blue slider, we see these rings to form as different homographies get performed on these rings. So you'll notice that a wide range of different distortions can be performed by homographies, and for that reason they're quite frequently used in computer graphics. Okay, and the other thing I wanted to show you quickly is that when we were looking at the two-dimensional projective plane, we saw a lot of conics, hyperbola, parabola, and things like that. And we saw many of them crop up, and we saw that they were also closely related to things like perspectivities and two-dimensional homographies. Well, for this reason, I wanted to show you the sort of three-dimensional analog of the of the conic, which is the quartic. Okay, so there are all these different quartic curves, and many of them look quite familiar, like the hyperboloid or the ellipsoid, and one can also find some more exotic ones. There's one known as the twisted cube, for example. Anyway, I just thought I'd give you a little sampling of these, just to show you some more of the interesting things which happen in projective free space.